Thank you very much, Georg. Great to be here in person. I will talk about some things that we did, some things that we're working on, and some things that we would like to do in project P12. So the things that we did, that's the past. These are the successes, of course. The present, the challenges, and the promises, the future. So in this project of TACO, we are interested in simulating rare events. And to do that, we use machine learning approaches. And this is what my talk is about. So recently, I helped to organize a workshop. This workshop at the beginning of September at the Lawrence Institute in the Netherlands. And the goal of this workshop was to talk about how to accelerate our ability to simulate, but then in particular to understand rare events taking place in complex systems. So for instance, look at this movie here that a student of mine made not too long ago, well actually quite some time ago. So this is a bottle filled with water, and this water is below 0 degrees Celsius, so it's super cooled water. Why doesn't it freeze? Well, it doesn't freeze because in order to freeze, it would have to form a nucleus, and that costs in free energy, so there is a barrier, and that's why it takes so long. Only if you shake it, something happens. Actually, this is something that was discovered by Daniel Fahrenheit 300 years ago. I thought that that this would be the oldest reference of this conference, but actually Anatol referenced Archimedes. So I think you want also the Klineman people, they could have referenced Lucretius, which would also have been an older reference. So the idea of this workshop is to find out how a process like this can happen, right? So this is this road here going up a mountain, and we would like to use computers. This is what's indicated here by this wireframe of this landscape. We would like to understand the landscape, and we would like to find this road that brings our system from one stable state to another. So when we wrote the application for this workshop to the Lawrence Center, we put in as one of the topics machine learning of rare events. And the other topics were reduced models, collective variables, acceleration of rare events. It turned out that, so we did this in 2019, in 2020 the workshop was postponed, and we had it in September. So between then and now, it turned out that basically all the workshop was about machine learning. So it's, at the moment, this is an incredibly dynamic field, and I think it's really great that in TACO we have machine learning as one of the main goals, to use it to understand surface reactions, because now is really the time to do it. We couldn't have waited longer. So there are of course many other rare events that happen in complex systems, like other nucleation processes like cavitation or melting, phase separation, transport processes, magnetic switching, chemical reactions, or here the very, very large group of biomolecular reorganization, which includes, I don't know, protein folding and many other processes. So here, in many of these, for many of these processes, we have to deal with the same issues. And of course, the prototypical rare event is symbolized by this free energy surface here, which has two stable states separated by a barrier. If this barrier is large compared to KT, then the system will stay here for a long time before it decides to hop over to the other side. So far, so good. But in a complex system, the first question that arises is, actually, what is this coordinate here? What is the Q? For nucleation of a crystal in a supercooled liquid, we know that the size of the crystalline nucleus is a good reaction coordinate. But what do we mean by good reaction coordinate? And does it capture all of the story? So this is an important question. And in order to answer this question, one can try to use machine learning. But there are many other challenges in molecular simulations. So in molecular dynamics simulations, that can be addressed with machine learning methods. One challenge, and we have heard a number of times about this, is how to represent potential energy surfaces. Of course, we can compute it ab initio, but that's expensive. So we'd like to use models that are cheaper to evaluate without losing much of the accuracy. There has been much progress in this area, following work of Behler and Parrinello in 2007. This is quite some time ago now, and they started doing this before everybody else was talking about machine learning. So I think this is quite pioneering work, and also the work by Gabor Csányi and friends has been picked up by many people. Also, Georg is working on this with his on-the-fly learning method. I think this is very important work because it kind of changes the point of view a bit. Here the goal is not to develop a force field. I think the question of Georg was also in this direction. The goal is not to explore as much of the space as possible, but to concentrate on the parts that are really important and to learn only that. But once you have the potential energy surface, you need to sample it. If you are not at zero temperature, this is very important. You need to sample the equilibrium distribution, or I mean, it could even be a non-equilibrium situation that you are facing. And this problem becomes particularly difficult if you are dealing with transitions between rare events, between stable states, when you are dealing with rare events. Another issue where machine learning can be very helpful is recognizing local structures. Once you are able to carry out a molecular dynamics simulation of, let's say, crystallization, you need to understand what's going on, right? You need to be able to distinguish local crystalline parts from disordered parts. In some cases, this is a trivial problem. But in some other cases, it turns out it's not so easy, and it turns out that you can use neural networks to do that. Others have developed unsupervised learning methods based on autoencoders for the same purpose. Now, I think this is really a difficult problem in a complex system, namely to identify reaction coordinates, to identify the degrees of freedom that really carry the important physics of a process, and separate them from other degrees of freedom that you can replace by thermal noise. There have been some efforts to use machine learning to address this problem, starting from the work of Ma and Dinner, who used neural networks to learn the committer. I will talk about that later, what that means, up to more recent work by Jung, Kovina, and Hummer, who used ideas of machine learning, of reinforcement learning, to combine the identification of reaction coordinates with the simulation of rare events. In rare events, you often have the chicken and egg problem, because in order to generate the training data, you need to be able to produce them, and in order to produce them, you already need to know what the answer of your problem is. So if you do that in a reinforcement, following a reinforcement strategy, that can be very fruitful. Also, the bare sampling of the equilibrium distribution is a difficult problem. What's the problem? I mean, you could say, well, we can do molecular dynamics or Monte Carlo. What's the problem there? But if you do such simulations, you are facing the problem of correlations, right? What you would like to have is a set of independent samples, but the molecular dynamics simulation is necessarily correlated. So you have to wait for a long time in order to get a new sample. A way out of this problem is the use of so-called, of generative models, like the Boltzmann generators of Noe and friends. This is a very promising approach. And I would say that if we want to separate these points here into successes promises, I would count the encoding of potential energy surfaces and the classification of local structures as successes, and the identification of reaction coordinate combined perhaps with the sampling of configurations, but also of trajectories. These are really promises, and we are actually trying to work into this direction. Now let me just then give you a few examples of these various methods that we and others have used to address these challenges. So this is something that we have heard about. Computing energies and forces ab initio is expensive, so a solution to this problem is to train a machine learning model like a neural network to predict energies and forces for a particular configuration. Now, this is an idea that is not particularly new. And interestingly, the first attempts to do something like that were in surface science. People were looking at small molecules on surfaces, concentrating only on few degrees of freedom, working with Cartesian coordinates. And that was a problem. That's the reason why these early attempts did not scale up to larger systems. Really a breakthrough in this whole story was the work of Behler-Parrinello, who suggested, instead of using Cartesian coordinates, to use descriptors that obey certain symmetry properties, like translational symmetry, rotational symmetry, and permutational symmetry. And by first translating the Cartesian coordinates into what we now call the Behler-Parrinello symmetry functions, and by writing the total energy as a sum of local energies of, in the environment of a particular atom, they were able to obtain a very efficient way to encode potential energy surfaces and make them applicable to systems of thousands of atoms. So and the accuracy that you get in such neural networks is really amazing. A former student and postdoc of mine who now works with Georg wrote a code that is freely available to do that interfaces to lamps, so you can really use it very comfortably to first train a neural network and then use it to carry out molecular dynamics simulations. At the moment, we are working on the implementation of long-range interactions together with Jörg Behler, actually using the method that he and Stefan Gödiger proposed. We should also talk with Georg, with project P3, to combine the on-the-fly simulation method with the neural network training. I'm sure this can be done in less than a month, so it shouldn't be a problem. Now, so here you see how well this works. DFT energy, this is the energy prediction of the neural network. The points are really on the straight line you want them to be. We have trained such a neural network for water and ice and for other substances. For the water and ice case, we trained, you need a suitable training set. We used liquid water and configurations taken from different phases of ice, and this is what you get in the end when you train with 7,000 configurations. The error is less than 1 milli-electron volt per atom. Now, these are training curves that Anatol would not particularly like, perhaps, probably because they actually level off. So what you can see here is the error in the energy as a function of the training set size. And you see that this learning curve here, the orange one, saturates. So at a certain point, you stop learning. This perhaps you find interesting. We wanted to find out how good the neural network can work to encode the potential energy surface. So the question is is the neural network flexible enough that we have here to reproduce the features of the potential energy surface? And to separate that error from the error that is introduced by the training procedure, which is not perfect either. So what we did was to compute energies and forces using the neural network itself. So we trained the neural network on neural network data. In that case, the training should be much easier, because there is at least one parameterization of the neural network that should reproduce energy perfectly. So indeed, the error that you make in that case is smaller, but it's not zero. I mean, probably if you keep on here, if you keep going, it should go down even more, but the neural network might get trapped in some locally minimum in parameter space. But what's important here, I think, is that this difference seems to be due to imperfections of the neural network. So it might make sense to work. Perhaps it's due to the missing long-range interactions. But this is something that one would need to investigate further. Anyway, so with this neural network, we were able to carry out simulations that you could not do with ab initio. We computed, for instance, density isobars, finding the density maximum of water at 4 degrees Celsius. We also computed melting points and found that for particular combination of functional with van der Waals corrections, you get melting points at zero pressure that are quite close to the experimental value. In order to get these numbers, we also carried out perturbation theory to correct for the errors that you necessarily make using the neural network. Now, these numbers they look good, but how good are they really? Turns out, this is I hesitate to say it, but it looks like a coincidence, because if you compute the coexistence curves in the phase diagram at higher pressures or at negative pressures, then you find quite, you find deviations from the experimental curve, which is this one, and the blue line here and the red line here are the coexistence curves that we computed by doing what's called Gibbs-Duhem integration along the coexistence lines here, and you see here that this pressure here, this coexistence line is too high and this is too low compared with the experimental data. The other lines don't. Forget about that. Okay. Now the method is efficient such that you can even simulate or compute the quantum effects related to the quantum nature of the nuclei, right? I mean, in molecular dynamics simulations, we usually treat the nuclei as classical, but in fact they are not, which is particularly important for light atoms. And here we did a simulation of water together with Michele Ceriotti and Binqing Cheng of water using path integral molecular dynamics. And what you see here is that the density isobars that you get for liquid water and for ice produce the quantum effect that is known from experiments, namely that the density goes up, or you should speak of the molar volume, because it's not the mass density that is studied in the experiments, but the molar volume. But this is a quantum effect that is also seen in the experiment, and that is only possible to do because of the efficiency of the neural network potential. So let me now turn to some results that are of relevance here in the TACO, in particular in the collaboration with P11 Backus. We retrained the neural network potential to include the vapor phase and the interface between the vapor and the liquid. And then we did simulations using slab geometries. And this is what we get out of these simulations. Let's first look at the coexistence density. So this is the density of the vapor coexisting with the liquid compared to the experimental curve. This is the dashed line. So you see that this the neural network produces a coexistence curve that is pretty close to the experiment. In particular, the critical point that you obtain by fitting this expression here to the data gives you a critical density and a critical temperature that is pretty close to that are pretty close to the experimental ones. If you compare it to the to ab initio simulations that were done for a smaller system by Schienbein and Marx, you realize that most likely the deviations that you see here and the simulations of Schienbein and Marx were done exactly for the same functional as the one we used, that the critical temperature that you get out of those data is too high, and that's probably due to the neglect of fluctuations, because in a small system you cut off some important fluctuations that become particularly important close to the critical point. Surface tension works well too, but this is just a way to check, right? Because we know what the surface tension of water is, we know what the coexistence densities are of water and vapor. But what's more interesting is what happens microscopically at the surface, and this is also the connection with the work of Ellen Backus. So first of all, if you want to do that, you need to find where the surface is. You have capillary wave fluctuations which distort the interface, so it's not a flat surface. So we use some methods to do that, and once we have that, we can study how molecules behave at the surface, how are they oriented, and we find something that is also found in some frequency generation spectroscopy done in the group of Ellen Backus, namely that you have dangling H bonds. You have a considerable population of molecules that have one non-hydrogen bonded OH bond sticking out of the surface. Okay, let me now. Do I still have some time, Georg? He's standing up, so this means I'm running out of time. So let me just tell you that classifying structures, that's an easy problem for machine learning. So traditionally, local structures are characterized using Steinhardt bond order parameters based on spherical harmonics. This works in some cases. In other cases, for instance, water and ice, does not work so well. The question is, can we classify structures based on the symmetry functions of Behler and Parrinello? The answer is, of course, yes. Because if they allow you to predict the energy, they should be easy for them to tell us about the structures, and this indeed works. So it's basically the same neural network that we have heard before, and you can use it to classify different structures of ice that's, for instance, formed in a liquid, and you see that you get very accurate. What these bars tell you is that you get an accuracy of 99% or so when you classify local structures. I'm sure that you can easily apply the same idea to other systems as well. Now, let me turn in the last 30 seconds to the problem of identifying reaction coordinates. This is a simple polymer model with short-range attractions and a hardcore repulsion, and this polymer has the property that it crystallizes, that it goes directly from a coil-like structure into a crystal, provided the interaction is short-range enough. And one question that you may ask is, how does this happen? I would like to find the degree of freedom that tells me how far the reaction from here to here has proceeded. I would like to find a reaction coordinate that, that tells me how far along I am. And so here the question is, what does that even mean, right? What does that mean? Well, a good reaction coordinate is a reaction coordinate that tells me what's likely to happen next. And this is exactly the committer, or the commitment probability, or also known as the splitting probability, is an idea that goes back to Lars Onsager in 38, that he used to study this ion separation. So the committer is a probability that starting from a certain configuration, you will end up in B rather than in A. And if this probability is 50-50, then you're at the transition state. And if your reaction coordinate parameterizes this probability, then it's a good reaction coordinate. So the question is how to find this reaction coordinate.
That's maybe shown next
time. This is the end. I'm coming to the end. So what we would like to do, and following ideas of Junkovino and Thoma, is to develop machine learning procedures to learn the committer, to use the information that we have learned to do enhanced trajectory sampling in a reinforcement cycle.
That sounds like a great cliffhanger.
That sounds like what?
A great cliffhanger.
Yeah, a great cliffhanger. So stay tuned. In the next conference, we will talk about that. Let me just, at the end, mention that I'm still looking for a student. So I have a great team together, and the postdoc will be funded by TACO will come soon. But I'm still looking for a student. So if you, I'm talking to the young people here, a friend of yours, smart friend of yours, would like to do a PhD in an interesting field, then just tell him or her and let me know, bring it together. Thank you.
Thanks, Christoph. Great. We will have time for one or two brief questions.
Very brief. You showed these phase diagrams, and all the functionals had a sort of the slope that the experimental curve had, but your neural networks had a different slope. Is there a particular reason for
you mean the phase diagram here of water that I showed? Yes. This one here. So, I mean, these 4 lines are coexistence lines computed with different approximations. If you neglect van der Waals interactions, then the coexistence lines have the wrong slope. Then you couldn't melt ice by compressing it. If you add van der Waals interactions, then they have the slope with the right sign. The experimental curve is this one. Yeah. The other lines that I showed are lines of density maxima. It makes this a bit confusing, but
Any other questions? Christoph, when you do this identification of the local coordination or environment, what happens at an interface or something like that in phase transition? Did you test this?
So yes, you can train the neural network to recognize the atoms that have, let's say, a crystalline environment on one side and a disordered one on the other side. So this can be done.
And then there will be few atoms at the interface that cannot be identified. Okay. Any other questions or comments? People are eager for coffee, it seems. Christoph, thank you very much for your contribution again. And can we reconvene 5 minutes late?